Hey everyone, and welcome back to the Lathe restoration. In the previous part we disassembled this Colchester Master 2500 and already cleaned the base of the machine. It is now time to get it back together, and then we're going to modernize this old machine. So let's get started. Of course, there are many parts to clean, so let's start with the saddle. Now in reality I cleaned everything you will see in this video in one go, which took me a few days. But I think it would be very boring to show you all of this at once, so for video purposes I will always show you the cleaning process of a part before we need it to reassemble the lathe. This way it is not always the same for 10 minutes. For cleaning the saddle I basically use everything, as it has painted, bare metal and precision surfaces. And it has all the main oil channels for the lubrication system. So a lot of elbow grease is needed for getting it back to life, and it was by far the most time consuming part of this restoration. The first step in reassembling is putting the guide rails back on. I cleaned all the small parts off camera, as this would be very boring to watch. I always make sure to give every bare metal surface a nice coat of whey oil to prevent rust from building up. The grips on the saddle are extremely hard to get in because of the spring clips. Therefore, I get them in before the saddle is back on the machine by sliding them in from underneath the spring clips. Since the bed is bone dry, I'm oiling everything to the extreme before installing the saddle. And it slides very smoothly. I roughly adjusted the grips so the saddle cannot lift from the waist and installed the carriage lock. Next up we need the apron, and this is again such a pain to clean properly, but at least I can really go to town with the Scotch-Brite on this one. And after a few rounds of scrubbing, it brightens up quite nicely. Here's a quick look onto the half nuts for engaging the lead screw. The apron has its own oil reservoir, which needs to be drained. And I was quite surprised that the oil still looked clear after so many years. But I'm degreasing it anyways to get all the residue out of the transmission. Even though this gets filled up later, I'm manually oiling every bearing surface just to be sure it is perfectly lubricated. Here's a look inside for you. This is the feed selector for apron or crosslight. And this is the lever for engaging the power feed. And it prevents you from engaging the lead screw while the power feed is engaged, and vice versa, which is really nice. We are ready for installation. I put a piece of wood on it to support it, and then I can carefully lift it up until the mounting screws start grabbing and pulling it up. I'm not tightening these up yet, you will see why in just a second. This is the lead screw. It is spring-loaded, so in case the shear pin snaps, the mounting plate can move out of the way. Next up, the feed rod. And the clutch shaft. On the other end of the bed, the lead screw gets a thrust bearing, and then the end bracket holds everything in place. It is precision located with a set of pins, and then it gets screwed onto the machine. Another thrust bearing for the lead screw, and then the bearings get preloaded by adjusting the lock nut. It must take out all the play, but not so much that it binds up the bearings. The clutch shaft gets just a set screw for eliminating the play. Sadly, this lathe is missing the threading dial, which would get attached to the right side of the apron. I will have to figure something out in the future. Last thing to install in this step is the shear pin, which is not the original one. And now I can tighten the screws down as the feed rod aligns the apron perfectly in line with it, so nothing binds up. The apron gets filled with whey oil, and I give the parts another coating as well. Then I install all the wipers and we can move on to the next part. The crosslight needed several coats of degreaser to get rid of the dirty oil that was stuck to the ways. But it is always satisfying when you can finally get a surface to shine again. I repeated the process a few times until it looked like this. The sides are easy to clean as they are not too dirty, but the top of the crosslight really took some elbow grease. Try to Scotch-Brite something for half an hour and tell me how your fingers feel, because mine were about to fall off on this. But man, the result is just worth it. Now we can get it ready for reassembly. Again, I'm excessively oiling everything, and if you wonder why you can't see any scraping marks, it is because these lathes were not scraped from the factory. They just left in very small 2 marks, which are still visible across the entire length of the crosslight. Here's the 2-piece nut construction for the lead screw. There's a central piece that gets pushed down with a set screw from above, which presses onto the small gips in the nuts, forcing them apart, which takes out all the backlash. So the mounting screws for the nuts get tightened once the assembly is back onto the machine. Next is a crosslight lock, and then the T-studs get inserted for mounting the compound later. One final coating of whey oil and we can install it. But of course the dovetail on the saddle needs oil as well, and here I'm using the built-in oil pump just to make sure it works properly. Now the lubrication system works as follows. The oil pump presses oil into the prism way at the front and then to this bore where it travels down the way, then into a channel at the bottom of the saddle and up to the crosslight way again. At the end there's a small bore at the side of the saddle where it comes out once it traveled all the way through, which gives visual confirmation that everything got lubricated and nothing is clogged. Let's slide the crosslight back on. Now I'm inserting the gib, and again this gets only lightly tightened for now. Next we need the lead screw assembly, which is held in place by a set of thrust bearings. Making sure the debris shields are facing the right way, and then the mounting bracket gets installed. Then the second thrust bearing, and the entire assembly gets pressed together by a lock nut. This needs to be adjusted just like the lead screw on the bed previously. I'm threading it into the nuts by turning the hand wheel, and then I'm screwing the mounting bracket onto the saddle, but only until it touches. Now for aligning everything, I'm bringing a crosslight all the way to the front so the lead screw has the most amount of support, and then I adjust the nuts for backlash in this spot as it has the least amount of wear. The nuts are now tight, so I crank it all the way to the back to align the mounting bracket, which can then get torqued down. Now everything is aligned and the gib gets its final adjustment. Back to cleaning. The compound was pretty much in the same condition as the crosslight, and I will just show you a few clips of cleaning it, as it's always the same. Lots of scrubbing and wiping. And here you can see before and after comparison. And after much work on the top, it looks like this. And of course, I cleaned the base as well. As always, lots of oil and the locating pin drops into place. The compound can only get assembled from the underside because of the lead screw nut that has to go through it. Otherwise, this is really similar to what you saw me do on the crosslight, just smaller. Alignment is good, so securing the nut in place with a set screw and it can get installed to the machine. I'm mounting it on a 29.5-degree angle, which is most used for thread cutting. But of course, this can get changed at any time. I made a small mistake on the hand reel and forgot to put a washer back behind it, but I catch it in time and pulled it off again. I know a punch is not the right tool for this. You would want to use a pin spanner wrench, but it only takes a few very light hits and I'm careful not to damage anything. And with the compound back together, we can start working on the last major component, the tailstock. At this point, I don't think I need to say much about the cleaning process anymore. I'm assembling the quill and make sure it is well lubricated. The first part to go inside the tailstock housing is the quill lock. I can then push the quill in from the back side because this way it is much easier to slide it over the lock, which must be in a specific position. The quill itself has a very tight fit inside the bore. Now to the rear end of the tailstock. First, threading in the lead screw, which gets thrust bearing, followed by the mounting plate. The hand wheel gets its dial back on and this dial is locked in place by 3 springs and bolts, so you can adjust the 0 position on it just like on every other hand wheel on this lathe. Fits nicely, and again I'm careful with using the punch, but in this case I wouldn't even know how to get the pin spanner in if I had the right size one. It operates very smoothly and the hand wheel has enough friction to stay in place. Securing the locking lever, and it is time to mount the bottom plate. The eccentric locking lever for the tailstock body itself needs to go in first, which is held in place by a set screw. Now the plate can slide onto the 2 pins, which are later used for precision aligning the quill with the spindle of the lathe. Then everything gets bolted together to secure it in place. Last thing is the clamp, and we are ready for installation. A bit of whey oil, and it slides onto the machine. Locking it works perfectly. Screwing the end stop back in so it can slide off the bed. The handle of the quill lever came loose, so degreasing it and applying a bit of super glue should do the trick. Testing it with a Morse taper free drill chuck, and it's looking very good. After installing the way wipers, the tailstock is finished. I slid the chip pan back in and reattached the sand stop for the carriage. It is not the original one, but fits the bed pretty nicely, so I will use it. I almost forgot about the chuck. I really wanted to take it apart, but the screws are so incredibly tight that I gave up on this, as I don't want to risk snapping one of them off, which would be catastrophic, as this is a quite expensive chuck. So just cleaning the outside on this one, and I'm only showing you a few seconds. Here it is all cleaned up, and after applying a bit of oil, it turns very smoothly again. Of course, I made sure to mount it in the correct spot. There is a mark on the back plate that refers to the right position with a mark on the spindle. Tighten up the 3 cams and checking for correct engagement of the cams, which is shown by these 2 arrows on the spindle. Alright, the lathe is back together, but we can't just turn it on yet, because after years of sitting around, the headstock needs a little bit of care as well. So, time for some maintenance. Taking the cover off reveals the gearing between the headstock and the feed box. I also took the motor cover off and removed the drive belts. The belt for the oil pump is hanging on by a thread and needs replacing. I cleaned everything, but I didn't film it as you have seen enough of me cleaning stuff. Before taking off the lid, I wanted to take a look at the foot brake. And this brake pad looks like it has never been used, as the spindle has a second brake inside the headstock that engages automatically when disengaging the clutch. If you step on the foot brake, it disengages the clutch first and then presses against the additional spindle brake. Now let's finally open the headstock. It has an additional plastic lid to seal it against the casting, and here it is. This is a clutch shaft that spins all the time, engaging forward and reverse and forward again. I'm wiping everything off as good as I can before spraying it with degreaser to get the residue off. For getting the old oil out of the tank, I thought it would be a big brain move to just undo the oil line and starting the machine with just the oil pump belt installed. This way I can get everything out of the machine and wash it out with a bit of new oil. The manual calls out for Shell Tellus 27, which is no longer available, so I contacted them, and the modern day equivalent is Shell Tellus S2M32, which is what I use here. It is very important to use the right oil as the headstock has high precision spindle bearings, and using the wrong stuff can cause them to overheat and get destroyed. And you really don't want that to happen, as these spindle bearings are several $100s a piece. The feed box uses the same oil, so we will do an oil change as well. The oil is coming out really slowly, so I helped it a bit by carefully blowing air into the feed box. Sealing it back up and then filling it until the side glass shows about 2/3 of height. I reassembled everything on the other side and installed a new belt for the oil pump. All the covers get reinstalled and we are ready to give this lathe its first run. Turning the motor on, and of course the chuck jaws are tightened down. That is very important, otherwise they can work themselves out of the spinning chuck and you don't want this to happen. And holy crap, this sounds awful. Let's hear it in reverse. Okay, something is clearly wrong. Did I just buy a broken machine? Well, no. Let me explain what's going on here. Take a look at the headstock drawing. This is the clutch shaft, and if we engage it forward, the power gets transferred to this small 26 tooth gear and then to the 39 tooth gear on the drive shaft B. If we take a closer look, we can see that this very fast spinning gear doesn't have a bearing. It is just riding on a steel shaft which will wear out insanely fast. This is such a big design flaw on an otherwise extremely well designed machine. I don't know what they were thinking. And while I was investing this, I noticed that the single screw holding this shaft in place was missing, which probably didn't help. But how can we make sure that it is just this one gear and that not all the other gears got damaged by this? Now, since this is a 3-phase machine, we can electrically reverse the motor by swapping 2 wires. Now the clutch shaft spins in the opposite direction, so by engaging the reverse clutch, we transfer the power directly to the 39 tooth gear while running the spindle in the forward direction. This way the 26 tooth gear still spins, but it is no longer under any load. And to be honest, this is how they should have designed it in the first place. But yes, this is quite a ghetto method and I'm working on a permanent fix for this. But reversing the motor also reverses the oil pump, you might think. And yes, that's correct. I checked how the pump is designed and it is a straight bladed impeller inside a symmetrical housing, which means it performs the exact same in both directions. If it was a curved bladed impeller, this would lead to insufficient lubrication of the headstock, but luckily it isn't. And I checked the real parts and not only the drawings. But let's see if this entire theory is actually correct. And thank God. This is how it should sound. This is such a relief knowing that it is only this single gear while the rest of the headstock is in great shape. Now the machine itself is pretty much finished. But the way it is right now, this machine is basically straight from the 80s. So let's modernize it by installing a digital readout. So of course I purchased the finest DRO money can buy. Yeah, it's an import. I'm broke. But to be honest, even these more inexpensive DROs are not exactly cheap. This configuration still set me back about $300. Mounting a DRO is quite tricky on this machine, so let's use my freshly restored mill to modify the crosslight. I'm drilling 6 holes into the side of the crosslight for tapping M4 threads. They get a nice chamfer before tapping them by hand. I'm also drilling another 8 holes into the top at the rear end of the slide. I want to make a T-slot attachment similar to the one that was an add-on back in the days, but since we are mounting a DRO to the side, the original design does not work anymore. I tapped the holes for M8 and as you can see, I of course did not drill them all the way through. Next we need to machine the brackets that will hold the X-axis scale. I use aluminum right here as it is more than enough for this application. I need 3 pieces, so after a quick trip to the bandsaw, I can take them down to final size on the mill. Now they get a few holes, which are for mounting it to the crosslight, mounting the scale to these brackets and mounting a cover later. There are 2 identical brackets for holding the scale and the third one will go in the middle for supporting the cover. A bit of tapping and we can install them. And as you can see, the crosslight is so low profile that this is the only way to attach a scale properly, at least in my opinion. But before that, we need to make more parts for mounting everything. This is really basic machining, so I did not film everything I made here. I need to drill 2 holes into the saddle, and this is as far as it travels, so this abomination of a drilling setup had to do the trick. I'm only drilling and tapping 1 hole for now. I can then mount a bracket and get it indicated in, so it functions as a guide for locating the 2nd hole. Now the bracket gets attached permanently and of course indicated in parallel to the crosslight. The scale can then get screwed on, and this needs to be indicated in as well. Mounting it this way lets the compound still swing 360 degrees while not taking away much of the max swing capacity over the crosslight. I made another bracket that will carry the reed head. Again, indicating it in before mounting. This took a lot of measuring, but it fits the scale just perfectly. Now to the backside for mounting the Z-scale. Another bracket, and here I'm able to use existing threaded holes and the machined surface they were meant for a taper attachment. At the front it is another bracket, just a bit longer because of the thread locations. The scale gets screwed on and indicated in, which I forgot to film. Now for connecting the scale to the reed head, I made this more complex plate. I can again use existing threaded holes, and I made it following the shape of the saddle. Just like on the other scale, the reed head gets screwed on, but this time I left the plastic liner in while attaching it, as this is a bit easier this way. This pair of brackets will be for cable management. Before tightening them down, this aluminum support gets attached to them, which will carry a drag chain. I got this high quality sealed drag chain, and after pulling the cables through, I made this part for mounting the end of the drag chain to the big plate I made. I'm gluing in a stud so I can attach it with a nut which is a bit easier to tighten from behind the plate than a screw. The front end of the drag chain gets screwed to the support so it won't slide around. And after pulling the access cable through, we can give it a quick test. Seems to work just like I hoped. The scale gets a cover to protect it from chips and other stuff like coolant that could work its way inside. The last thing on this plate is securing the cables so they can't pull on the reed heads. You can see 2 empty threaded holes in the plate, and these are for adding flood coolant in the future. For covering up the crosslight, I need to fabricate a custom cover. This is 3mm thick steel to make sure it can withstand something like a heavy tool that gets accidentally dropped out of the tailstock, for example. This is what it will look like, but so much welding on this amount of material always causes a bit of warping, so I had to grind on it quite a bit to get it back into shape. I drilled a few holes off camera and this is ready for installation. You might notice that the oil reservoir screw is in the way of the scale, but don't worry, I got something on order. I just threw the display onto the machine where the lamp used to be attached, because I can only decide where I want it to be once the lathe is set up in the shop. So let's try it. The last piece to make is a small bumper. For cutting plastics you would want a much sharper cutting tool than what I'm using right here, and I bought a few very nice turning tools, but they are all too big for this small tool holder, and at this point the new one had not arrived yet, so I had to use what came with the lathe. With the DRO I can roughly measure the diameter and set the display accordingly. I forgot to record the finishing pass, so next is drilling a through hole and a counter bore. A bit of deburring, and here comes the parting blade using power crossfeed. The bumper is finished and it protects the tailstock from ramming into the DRO parts. Now this is a prototype of what I have in mind for the T-slot attachment. And yeah, I effed up pretty hard on this, because I misplaced 2 of the holes in the crosslight by 1.6mm, which is such a bummer, but I'm not a guy who tries to hide mistakes. It is what it is. And the screws are still a bit too long, because I haven't decided on the height yet. Here's the solution for clearing the scale. Just a 5/8 set screw, and I deformed the top thread a bit so it can't accidentally get screwed all the way down and fall into the transmission. And this is the final product. My multifix tool pause arrived, which is just attached with the small stud from the original one, because I was impatient and wanted to see how it looks. But of course this needs a proper one. Alright, the project is finished, at least for now. But of course we still need to evaluate the mechanical condition of the lathe. So, time for inspection. What you want to know on a lathe is its total spindle runout. A quick wipe down so everything is clean, And then we can bring an indicator in. The machine is set to its lowest RPM, which is 30. Okay, this is a precision machine. We need the big guns. This is my 1 micron indicator. That is 0.4 10,000ths of an inch, the most precise thing I have. The GoPro has a hard time focusing on the dial, but it reads a low spot of maybe 3 microns. Let's try a different spot. I guess now I know why the spindle bearings are so expensive. And just for curiosity, let's measure the phase. I'd say maybe 4 microns. Absolutely impressive. So I think this about wraps it up. Of course, there are still things I need to address, like the tool post stud, the missing threading dial, and of course, the headstock problem. But that's something for another video, so stay tuned for that. Anyways, I really like how the lathe came together. I hope you had fun following along, and thanks for watching.